first speaker is Dr. Chris Chantler. He started his university work in the bachelor's degree at the University of Western Australia. From there he went to Oxford, where he got a D.Phil. Any other university would call it PhD, but not Oxford. Oxford is special, so he has a D.Phil. From there, he went to the United States, to Washington, the National Bureau of Standards. They don't call them any longer, they tell it in French, so I can't tell you, but that's what it means. And then he came back to Australia. He's been here in this school for 5.5 years, working in the optics group, which is where he can combine both experiment and theory, and he has been studying and working on the topic of tonight's talk, quantum electrodynamics, for some 20 or more years. So I ask you to welcome Dr. Chris Chantler.
About this particular series of July lectures. There are 4 of them. They're all working around the issues or some of the most significant features of quantum mechanics. Jeff Oakman, 2 weeks ago, started the ball rolling with a general survey of some of the impact of quantum mechanics, particularly as this year marks the centennial of the founding of quantum mechanics by Max Planck, and all the changes and dramatic that has led to. Last week's lecture by Dr. Rob Schulte worked on, if you like, modern developments of technology. Not so much how they're transforming the world, but the opportunities that they can lead to. And today's lecture, if you like, is on the single most important, or single most impressive, perhaps is a better word, development of quantum mechanics in the modern era, and as the subtitle says, the most accurate theory in the world, which certainly bears some discussion, argument, debate. Maybe there'll be some questions on that in the end. The next lecture, next week, will be on quantum computation. New, recent research, very high profile research, quite significant contributions and funding from across Australia and in the United States on this in the last couple of years, and all of the different sorts of problems that have to be dealt with in understanding how you can use quantum mechanics to design a different type of computer. Now, I was asked to give 2 small notices. There are some queries about Jeff's lecture notes from 2 weeks ago. There are just a couple of copies left over, and they'll be down at the front at the end of the lecture. And the other comment was that for Dr. Schulten's lecture notes, you can actually find them on the web. There's the web address. Basically, if you find the University of Melbourne and the School of Physics, then use Rob Schulten's name, and you'll find it fairly quickly. You'll see the notes in there. Very good. So, I'll just leave that up there for the moment, just to give a bit of a frontispiece or to remind people what on earth we're here for. Basically, I want to talk about quantum electrodynamics. And I guess that's really the core thing, the core development of quantum mechanics, which explains how light interacts with matter. And one of the key features of it is the superb accuracy that can be gained by some extremely precise tests and measurements. These measurements are not necessarily just used to test it, they're used for a lot of other purposes too. I'm not going to emphasize applications very much in this talk. I'm going to really concentrate on giving you some kind of feeling for how the theory is developed, what some of the ideas are behind it, facing us, either in research or in understanding the physical world today. I kind of want to link together two threads. One thread is a general interest in inquiry and new understanding. What sorts of questions should we ask? How do we get to a useful answer? And I want to start that back at some kind of beginning. And my two threads, roughly speaking, are going to come from, initially, from the ancient Greeks. 640 BC, Thales found that if you took a piece of amber, which is that brownish resin glass, which often has fossilized insects in it, and you rub that with a piece of cat's fur, then you could use the amber to pick up pieces of paper or other things like that. Now there's a modern development of that, and I have that down here. You might ask, we have to have some pretty useful applications and high technology applications. That's extremely important. So, this is a sort of party trick, which actually really goes back to 640 BC. So you can say it's not a very old trick, except for the actual rubber of the balloon, but at least it's a good place to start. Obviously, our interpretation is that we've rubbed off some charges. We've transferred charge from balloon to jumper, in this case, or from jumper to balloon, and that means that you have an excess of charge on the insulating balloon, and there are dipoles in the insulator, in this case of the door, which attract it. In other words, we're talking about charge. This is one of my threads here. I want to talk about charges and things of that nature, and how that has led to an increased understanding. Of course, the development of that didn't progress that fast, I suppose, if you think about it from that perspective. And it finally arrived at Coulomb's law in about just before 1800. Coulomb's law simply explaining the force that you could get on charged particles separated by some distance of a radius r or a distance r, and one charge q1, one charge q2.
Excuse me, I think light's not interacting very well with makeup in that particular scene there.
I think that might,
That's a little less light might be helpful.
that might be helpful. Very good thinking. But that itself was a major achievement. At the time, Coulomb didn't have a value for that constant. He only said it was proportional to q1 to q2 over r squared. And that's been developed quite a bit since then. Similarly, the compass is a very old invention, or at least the concept of magnetism and of pieces of magnetic material is a very old invention or discovery. Chinese in the 13th century BC knew something about it, and the Greeks on the other side in Magnesia, which is where the word comes from, found that magnetite attracts pieces of iron. The typical legendary thing is that you had this shepherd who was walking along with his stick, and his stick, which had some metal on it, got stuck with a piece of magnetite that was coming out of the ground. Whether that's true or not, it's certainly another ancient piece to this puzzle, which we've been piecing together for some time. That, of course, leads to the concept of electricity. Now, this particular area, Jeff Opak gave quite a long discussion of in terms of the sorts of modern inventions that have come out of our new understanding of electricity. Our radio, TV, hi-fi, fridge, and so on. But, I might even turn that off. But the basic idea is that magnetism with electricity, the electromagnetic force, is one of the four natural forces of nature, together with gravitation, the strong nuclear force, and the weak nuclear force. The strong nuclear force keeps nuclei together. The weak nuclear force leads to, in its most obvious side of it, leads to radioactive decay. And so between the four of them, we think we have a reasonable understanding about what's going on. However, the most obvious of these forces is, of course, the force of electromagnetism. It's the most recognizable force in our lives. It holds solids together. It stops me from falling through the floor. It holds my head up against my body, for example. Stops the force of gravity pulling me or flattening me. It's at the core the basis of all frictional forces and all chemical reactions. So if I say that at some point that development of an understanding about, if you like, pure electricity was a major boon to current society, the place where you generally see the most exciting display of that is in a flash of lightning in nature. And just to give you a couple of pieces of information about the background of that, you've got charge accumulated in a thundercloud before lightning strikes of around 40 coulombs. There's an instantaneous current as that arc goes down of 20,000 amperes. And the total electrical power generated by thunderstorms around the world, basically continuously, is about 6 by 10 to the 8 watts. Large potential difference, large number of thunderstorms, and significant average current. They're very powerful things, and in fact they're a major dynamic about atmospheric storms, atmospheric physics. Now if I say that, okay, lightning of course was there even before they knew about amber, but the link between the two, the concept of actually beginning to understand what was going on, really relates to Benjamin Franklin, 1752, and he demonstrated with some not that safe experiments that lightning was ordinary electricity and you could attract it in various ways, and you could avoid killing yourself in various ways. And of course he named positive and negative charges, and that in the end led to Maxwell's equations some 100 years later. This is a differential form of Maxwell's equations, the way we tend to use them most now. I'll turn the lights on again. About that much. Now, you could ask what sorts of experiments Benjamin Franklin either might have wanted or might not have wanted to do. And if we imagine that this is he, that wasn't quite what several of you will have noticed, that if you are actually out in a very strong electrical storm, or if you're at the top of a mountain when a strong storm is going on, then you will actually start to get sufficient traction that your hair will tend to stand on end, things of that nature. What he really wanted to do, though, was to attract lightning. Not necessarily quite like that. But effectively, this is just the same. We have a large potential difference on the Van de Graaff generator. A collection of positive charges is collected by separation of charge at the bottom by travelling along an insulating belt, and then goes to the outside of that conductor. And the charge accumulates to the point where the electric field is sufficiently strong between the large ball and the small ball that the air can ionize and the charge, positive and negative, can travel in opposite directions and neutralize the system. Now in that sense, this is a very powerful side of electricity. And it's also kind of interesting and it's also very useful, but it has its limits. So if I talk about those limits just a bit, if I summarize that as being basically 19th century classical physics, I could explain many observations. We've just explained a couple of the observations it can explain. The basic concepts were that if you had particles, they would obey Newton's laws of motion. If you had radiation, it would obey Maxwell's equations, electricity and magnetism. Waves would obey Maxwell's equations. And that worked very well. If we extended classical physics by including special relativity by Einstein in 1905, we actually just got into this century, or should I say the last century. words, we had a new understanding for a new constant of nature. Every one of these constants of nature told us something really profound and fundamental about the way life is, the way physics is, the way the universe is. So this was a major development. Of course, if all velocities of all objects are much less than the speed of light, it didn't make much difference, really. But if you want to explain any kind of electric current, rockets, synchrotrons, and lots of other things, you have to have special relativity, otherwise you can't explain it. I want to talk about things which you can and which you can't explain as we go through this talk. Most importantly, despite special relativity, there was still no explanation of how light interacts with matter. Right, that's a bit peculiar. In the 19th century, there's lots of things that you could do with matter, lots of effects that you can see involving matter, flames, and all sorts of things. But if I say, how does a radio work, TV, hi-fi, light bulb, things of that nature, even a flame, there wasn't a proper understanding about why something happened. If it was static and stable, we could say, well, that's static and stable. But if it's actually moving, it's actually interacting, we've actually got light coming in or going out of something, then the explanations were largely absent. The first sign that revoked that sort of approach, or alternatively gained the insight to try to understand what was going on, was of course with Planck and black body radiation. This is a black body radiation curve here. You can see wavelength along the bottom, it's a little bit small here. And you can see an intensity or strength on the side. And you can see that you can go through a range of wavelengths, and if you have a black body of a particular temperature, there's the temperature of the sun, then you get a peak in the distribution in the range of visible wavelengths. If you change the temperature, then your distribution is smooth and continuous, but it changes. This was experimentally observed, but it disagreed completely with everything about classical physics. And Chip has already told you about this, so although this is really an independent lecture, I'll try and be brief. One thing which is a little bit different is if I look at a light bulb, it's not thermally fluid, not at all. It gives off a lot of heat, and 98% of it, of the power that goes through the resistor, or the tungsten wire, in the light bulb is given off as heat. The other 2% is given off as light. Having said that, if you look at the spectrum, you find that it is pretty much exactly a black body spectrum. In other words, all the normal common things, like this flame that give off light, you can talk about as being a black body spectrum with a certain temperature, even though it's not in thermal equilibrium. Now, the classical picture would have seen this curve go up to infinity, and that wouldn't have actually made sense. It would have got cold very quickly, things of that nature. Planck, in 1900, proposed and explained the shape of the experimental curve by saying that there are a bunch of oscillators in this black box, if we're talking about a black box, which had quantized packets of energy. And those quanta of energy were related with Planck's constant and n, which is like the number of the oscillators, to the frequency of the radiation. What that meant was if you had too much energy in any one single oscillator, it wouldn't oscillate. There wouldn't be enough energy for it to oscillate. That's a very odd kind of a statement. The next major development, of course, was in 1905 with the photoelectric effect. And here's a diagram of it. And the basic idea behind the diagram is that you had to have a certain energy of something, like your light coming in, or if you like, your wavelength had to be of the right type, so that you could actually excite a photoelectron from a piece of metal. Einstein in 1905, this is why he got the Nobel Prize, not for special relativity or general relativity, but for photoelectric effect, showed that light was composed of discrete particles, and then photons, of course, of particular energies. E equals hv, h nu, and here's insulated by C overloaded to the wavelength. So, as a short summary of what quantum mechanics really showed, energy was quantized and light had a particulate nature. They were the crucial observations of the turn of the century. If I go to another step, spectroscopy had been developing for hundreds of years. And with spectroscopy, there were a whole range of observations that most of the light, a lot of the light that we see, is not continuous in nature. In fact, a lot of it was discrete. If I take a particular example, here I have a sodium flame. Behind the sodium flame is a grating, which, just like Newton's prism, separates the colours, so you can see a spectrum. And you do not see a smooth, continuous spectrum of all wavelengths. What you see is a sodium doublet. It's a little bit hard to see the doublet there. There's actually two different lines. And this is a particular colour, sort of reddish. And if you look for the blue bit in the continuous spectrum, it's not there. If you look for something else over here, deep red, it's not there either. Particular frequencies, particular lines. Now that's an emission line. If I then find the switch, it might be this one. And if we do that exactly right, the white light also is coming through that prism, and white light is continuous. It's a bit like, it's actually a light bulb. It's like a continuous black body spectrum in the background. Now, against that, you see that sodium line that we had before is now, you can see a little bit of the sodium line itself, but you can also see a bit of absorption. You see a kind of absorption line there. So if you have a large amount of light going into that sodium vapor, it gets absorbed for a particular frequency. If you just have that sodium vapor on its own, there the black line is coming out a little bit more clearly. If you see the sodium on its own, then you see the light that's emitted. You see an emission spectrum. In either case, it's telling you something characteristic about the atom. Now we haven't got very far. We haven't actually even got the quantum mechanics in full. We've only got the ideas behind quantum mechanics, but that's part of this lecture, so I guess that's okay. But a sodium atom, simple as it looks just there, didn't make sense to spectroscopists for a long time. They looked at mercury, they looked at other things, they were too complicated. It was only by looking at hydrogen, the simplest spectrum, atomic hydrogen, that they were finally able to see a pattern. That pattern led to the Bohr model in 1913 and was summarized by a couple of statements. Firstly, that you actually had discrete electrons, charges, negative charges, orbiting a central, heavy, positive nucleus in circular orbits. Instead of an infinite choice of radii, only certain orbits were stable. These stable orbits did not radiate energy. That was something that was missing from the classical theory, which would always radiate away the energy. And so you wouldn't have anything discrete. You'd have a continuous spectrum, but also the energy would come off very quickly. And it only gave off energy when making a discrete transition to another stable orbit with a transition energy of E equals h nu, which is the difference in energy between those two states. And stable orbits are defined by quantization of angular momentum. You've got quantization of energy, which simply means you've got photons, discrete packets of energy carrying energy away. And also, these stable orbits satisfy another relation involving what's called angular momentum. Just a simple classical definition of angular momentum, which is to say that if you go around a full orbit, then you've got L, which is just cut off a little bit there, being equal to momentum times radius. And that had to be nh bar, or nh over 2 pi. A discrete multiplier of that, where n is any integer. could have a look at some other bits of maths there which I just put up for completeness. But you'll get these transitions, and you've got transitions which explain a lot about the hydrogen spectrum, and then about other elements as well. The problem with that is it was semi-empirical. We saw a pattern, or Bohr saw a pattern, and he found a relationship for it. Found a relationship for it, and from that relationship he could interpret this as being something about the structure of an atom. But it didn't explain why certain orbits should be stable. It said certain orbits appear to be stable, which was true. It didn't say why they should appear to be stable. So that, at that point, was a mystery, and it was only solved by quantum mechanics. Now that's starting to irritate me a little bit by chopping off the... So I go to backup system number 2. With quantum mechanics, the next major observation was that with 1924, so that's quite a few years later, Prince Louis de Broglie, with his thesis, showed that not only did light waves have a particle nature, but particles had a wave nature, had a wave character. Immediately following on that, we had both Heisenberg and Schrödinger developing two alternative conceptions, matrix mechanics and wave mechanics, which is what we call quantum mechanics now. And if I try and summarize that very simply, it says that any kind of a system, an atom, a metal, solid, bunch of electrons, electromagnetic system, any kind of a system is completely represented by a complex wave function psi. These are the rest of the postulates of quantum mechanics. It says that it's linear. Jeff Hofack talked about these. I'm only presenting them. Because I want to get beyond quantum mechanics. I don't want to say quantum mechanics. So you could measure a number of dynamical variables, and they must yield one of the eigenvalues of a corresponding bit of maths operator. You could make a series of measurements on them. You get a series of answers which would depend upon what the possible quantized eigenvalues were. Most importantly, and I guess the only one I really want to concentrate on today, is that if you look at the time evolution of that wave function, what's the time evolution? That's what's happening to the atom. Is it doing anything? Is it, for example, having one of its electrons going from a stable state to an excited state? Or back again, with the emission of a photon, or the absorption of a photon? That dependence is given by the time-dependent Schrödinger equation, complex. It's got Planck's constant there, minus IH bar, partial derivative with respect to time of this wave function equals some kind of Hamiltonian operator times psi. That Hamiltonian operator is kinetic energy plus potential energy, roughly speaking, in operator form. So if I'm talking about quantum mechanics in the standard sense, that's what I'm talking about. But now it's time to go beyond it. Because fairly soon after, the conception of quantum mechanics in that non-relativistic form was shown to be not adequate. In particular, if you're looking at an atomic system, which was one of the most relevant systems which led to quantum mechanics, that's where those discrete lines in the spectra came from, then those electrons are actually traveling at relativistic velocities. Velocities which are a significant fraction of the speed of light. So if I then look at that, there were approaches to try and get around this, to try and formulate a relativistic version of quantum mechanics, so-called relativistic quantum mechanics. Very soon afterwards, 1926 and 1928. So there's a time-ordered equation which doesn't apply to electrons, so it's not that relevant to the immediate discussion at the moment. And then 1928, the Dirac equation, which does apply to electrons. And in that, the time evolution of psi is given by, that looks the same, but this certainly doesn't. This is a moderately complicated mathematical entity. It still has a nice, simple energy eigenvalue as the answer for a hydrogen atom. So although it looks perhaps peculiar, these are two different notations. Although it looks peculiar, and although it's actually not the same as non-relativistic quantum mechanics, it doesn't give the same answer. It does actually agree with the experiment. Much more, much better. It's really the same kind of thing as the introduction of special relativity to Newtonian mechanics. Now what that led to, roughly speaking, is the fact that essentially all the properties of the elements of the periodic table are explained by how specific wavelengths of light interact with matter. Absorption occurs as you go from one quantized state to another quantized state, you get discrete energies. And if you know what those discrete energies are, if you can measure them accurately enough, then you find out something new about the structure of matter, something new about how the universe operates. So if I look on this side at Bohr theory, pre-quantum mechanics, then I'll see a series of transitions. Those transitions are quantized in the same way that quantum mechanics later concluded and give similar answers, and they're really quantized by two different numbers. The principal quantum number n, and also the angular momentum I mentioned a little while ago. An angular momentum states are called S, P, and D, so you can have a 1s state following certain rules, a 2s state, 2p, a 3s, a 3p, and a 3d. These are all states, and there are also rules about what kind of wavelengths of photons you can get, or in other words, what levels you can have transitions of photons between. If I start off with Dirac theory, being the relativistic equivalent of quantum mechanics, then if I look at the principal quantum number of 2 and 3, then there are a couple of levels. An S level and a P level have the same energy. Another P level has a different energy. And if I look at the n equals 3 level, you've got an S and a P level with the same energy here, and a P and what's called a D level with the same energy here, and another D level with a different energy. So when you look at the rules, you find that there are 5 possible wavelengths that you can get out of the system, 5 possible discrete wavelengths. The Dirac theory would give you a spectrum in frequency that looks like that, following certain rules. And that actually stayed as the basis for how people understood what was going on for a good 20 years. But then it was noticed in a particularly nice experiment that that wasn't quite what happened. And that if you look carefully enough, that S state and that P state didn't actually have quite the same energy. This was the first sign and the first demonstration that relativistic quantum mechanics was incomplete, was not adequate to explain the structure of, if you like, the wider universe, or if you like, the smaller details about the atom. It came from looking at how light interacts with matter. And it led to quantum electrodynamics. Now, in order to get to that point, which is in the 1950s, there were a number of particular problems. Previously, experiments had been done on the most obvious visible transition that could be seen, which goes from the principal quantum number of 3 to the principal quantum number of 2, and it's like the strongest transition of those ones. And for that, Dirac theory appear to be fine, appear to work very well. Part of the reason why it appeared to work very well was because at room temperature, your atomic systems and your electrons are oscillating because of thermal impacts, thermal motions. That Doppler width was almost the same magnitude as the sort of differences between those two strongest lines. And so because of that, it was very hard to work out anything in fine detail on that spectrum. That was resolved by Lamb and Rutherford in a famous experiment in 1952. In there you took a hydrogen atom beam, so not a hydrogen molecular beam, but a straight atom beam, a single atom. They were excited to a higher level, and the S state of that higher level was detected using Einstein's photoelectric effect. There are a couple of details here which don't concern us directly at the moment, but I've put them up again for completeness. You had to have a magnetic field there to separate the components of the states so they had different energies. You put in a very low energy radio frequency oscillation of an electric field, which actually allowed a transition between those two states that would otherwise have no energy between them. And it was found that there was a resonance between the two of them when that frequency was exactly the difference between the actual energies of their levels. In other words, that they were not at the same energy, they're at slightly different energies. So in other words, by measuring that frequency difference between those two levels, you can actually prove that there was a separation energy, and you can actually prove that track theory was wrong. It's also proved that QED, that had been developed just before then, also was able to explain this. Now there are some key issues regarding what quantum electrodynamics is, and that's really tying the threads of my discussion today together. Quantum electrodynamics is what's called a quantum field theory. That means, following Feynman and others, that the radiation field is quantized. Well, of course, we'd already got somewhere to that by saying there are photons. In a sense, you've already got quantized photons in quantum mechanics. But in a quantum field theory, you have something else. If you think about a simple harmonic oscillator, a pendulum swinging on the end of a string, it swings with a certain period. If you look at, if you like, the base position, the base energy of such a system, then there remains, in a quantized system, a 0-point energy, which means that effectively, even if you've got no photons, you've got a simple electron and a simple proton for a hydrogen atom, with no photons, then there's still what's called a 0-point energy, a fluctuation in the vacuum. Even if you're not surrounded by matter, even if you're in the vacuum of space. So even in a vacuum, there'll be fluctuations of energy because of fluctuations of the electromagnetic field, causing the electron to oscillate and smearing out the charge. Now, if you have an actual hydrogen atom, so you have a bound electron in a potential that looks a bit like this. This is where the nucleus is. Your electron actually has a wave function and is spread out over space, but has a certain amplitude of being, say, here. But if there's a field which is non-uniform, namely this potential here, and you have fluctuations of the potential due to this quantization of the field, then the electron oscillates, if you like, backwards and forwards. And by oscillating backwards and forwards, it sees a different binding potential, and you get a shift of energy. That's the so-called Lamb shift that led to this S state being higher in energy. Now, in fact, the effect is largest for one of those S states. What's an S state? It really is just a solution, one of those eigenvalues, one of those eigenfunctions of quantum mechanics, where the probability of finding an electron at every given angle is uniform. It's smooth. But there's another feature about it too, namely that there's a finite probability of finding an electron right at the nucleus, right at the origin. Right at the origin, if you have a probability of finding an electron here, but you have this oscillation which moves it backwards and forwards, instead of being up here where it's going down in potential a little bit, more binding, and up a little bit, so it sort of averages out. Here, it's less binding if you go this way, it's less binding if you go that way. So as a net result, there's a significant energy shift due to this effect. The most obvious two places where experiments have been done on this is the so-called G-2 experiment, talking about the gyromagnetic ratio of the electron or measurements of angular momentum and rotational angular momentum. And also the Lamb shift, which is the energy difference between those two states. The first one that found anything was, of course, the Lamb shift. If I mention a second key point about QED, then effectively you can think of this fluctuation as being due to the appearance of an extra photon around the electron and the nucleus. There are Feynman diagrams that look a bit like this, where you've got the electron coming along like this, and then one of these effects of this quantized radiation field corresponding to zero-point energy happens, and you effectively see a photon coming out and then going back in again. So for a period of time, you've got an extra photon. The system has changed, the energies are shifting. The other main type of this effect is you have the electron traveling along. It's called vacuum polarization. You have a photon coming along, and then for a time you have an electron, E minus, and a positron, E plus. So you have a polarization of the charges around the electron and the proton. The stronger the electric field, the more significant these things are. So that's a very simple, well, a very short, at least, a very short, brief summary of a couple of the key ideas in quantum electrodynamics. But perhaps it's more important to say how it had arisen in terms of the experimental insight and the spectroscopy of the levels. They're kind of intertwined. It's easier to give a bit of an experimental story than to try and give a detailed theoretical story. And this is a little bit of a challenge at this side for this sort of a July lecture. However, it's better to try and get a little bit across than to fail. So I want to talk a little bit about issues about the theory. This theory was completely unlike the Dirac equation. This theory was completely unlike Schrödinger equation. Completely unlike either relativistic or non-relativistic quantum mechanics. Here are a couple of problems with trying to use this theory. Unlike the Dirac equation and unlike the Schrödinger equation, QED is not analytic, even for the simplest bound system of a single hydrogen atom. That means if you try and get an exact analytic answer, you fail. You can't get an analytic solution. Whereas for the Dirac equation for a single hydrogen atom, you can get a solution. And you can write it down. You can stop numbers. It's exact. Secondly, each system involves a calculation of energy shifts due to any number of virtual photons. These extra photons that come into the field because of the quantized field theory. What that means, because you can have any number of them, you have an infinite series of Feynman diagrams, getting more and more complicated. Each one of these are, if you like, two of the simplest ones, but they get more and more complicated with more and more of these extra photons. That series is a series in order alpha, the fine structure constant, 1 over 137, and it's called asymptotically divergent. That means that if you keep calculating more and more complicated things with more and more of these photons, coming into the field and then going out of it. You get to the point where it diverges. It gets the actual numbers that you start to calculate getting larger, but you've still got an infinite term in your series to calculate. And actually it exceeds current computational power. Whether a quantum computer will solve that is another question. But at the moment, it certainly exceeds current computational power. If you've got multi-electron atoms, you've got an additional expansion in 1 over z. So this is additional mathematical complexity, making the calculations very difficult. If you isolate yourself to a single Feynman diagram, that also represents an infinite series of terms with higher orders of charge density, rho being the charge density, which is proportional to the element atomic number and that alpha again, 1 over 137. So QED is very much characterized by this constant, the fine structure constant, alpha. It's a crucial part of the theory, just like C was a crucial part of special relativity. And even for low z, sometimes people say, well, as z approaches alpha, like if you go up to an element like uranium, you expect this series to be extremely difficult to try and calculate. But in fact, there are even difficulties if you're looking at something like hydrogen. And worse than that, if you look at an individual term in this, it gives a result which is infinity, which is extremely unhelpful. Now, because of that, there's been several centuries of development of procedures to try and understand how to deal with all of this. And the progress has been developing, but it is already, in the very first years, fantastic. And now the procedures are called renormalization and regularization, and they end up with a determination of a finite result that you can then compare to experiment. But the procedure itself is really quite complex. And I'll give one kind of schematic example of that. If I wanted to calculate the third order corrections, so I said there was an infinite series. If we looked at not the first one, the second, and the third one. So we've got 3 photons here. 1, 2, 3. So that's why it's third order. In order to calculate the magnetic moment of an electron, how it spins around in a magnetic field, you have to calculate the answers to 72 Feynman diagrams, and here they are. And none of those is very pleasant. So actually a lot of physicists have responded with something that's a little bit easier to understand. And basically, here's the laboratory of some quantum field theoreticians. And they've got some of these ugly, rotten things on the board that they haven't been able to solve. And they've got all these infinities wandering around. And the cleaning lady has come in and is solving their problem for them. This is called renormalization. When you come to the bit that you can't deal with, you renormalize it. It's a little bit unsatisfactory in that sense. But if I say that that's a kind of complex difficulty of the theory, I then have to come to one of the other key features that I wanted to talk about in the talk, which is how accurate is it? If we call that a fiddle, which current modern theoreticians would not call fiddle, but some other current scientists and current textbooks are certainly not that happy about. Then we can go to Roger Penrose's book, The Emperor's New Mind, and a couple of the other books that he's published, where he points out that QED, quantum electrodynamics, and general relativity are the only 2 superb theories of modern science. He quantifies and he explains what he means by that. What he really means is that their ability to make accurate and precise predictions of systems that you haven't looked at before is phenomenal. That's what he really means. If I look at the specific accuracy of general relativity, then Einstein in 1915, of course, developed general relativity. And that's not the topic of this talk. But there are now tests of general relativity, which, if you like, you could argue are accurate to 10 to 14 significant figures for certain selective tests. But if you then ask a different kind of question and say, how do you compare general relativity with, say, one of the alternatives to general relativity, of which there are actually many, then you have to test what's called these so-called post-Newtonian parameters. They've only been tested to a fraction of a percent, so if you like, 2 or 3 decimal places in general. If I look at one of the other main theories of modern science called the electroweak theory, which is sort of like a development of QED, but to include that weak nuclear force. Various Nobel Prizes were awarded for it, and just last year, Carl Feynman was able to measure this to 1% for the first time. A beautiful and fantastic experiment, but only 1% measurement. If I look at quantum chromodynamics, then that's of order percent. If I look at a completely different field like biology, let's say we take the concept of Mendelian genetics or evolution. Well, you can argue about what the actual percentages that any of these can be tested at, but roughly speaking, there are lots of problems, including and involving control of unknown variables in determining it. Doesn't mean we don't accept them, doesn't mean that we don't believe them, doesn't mean we don't use them. It does mean that we haven't tested them, and they're not nearly as accurate or reliable, roughly speaking, as either general relativity or QED. So where's QED? One part in, actually my title was wrong, I'm sorry. In the last month, an extra naught's been added. So now I want to give you a little bit of a feeling for what that means and how it came about. In 1957, which wasn't that long after the Lamb and Rutherford experiment, the statement was made that the Lamb shift is thus an excellent confirmation of present-day quantum electrodynamics and of the relativistic theory of the electron. What that's really saying is, if we want to talk about how a photon interacts with matter, or what sort of wave function an atom actually has, or what sort of wave function a system actually has, then QED actually gives you the best answer for all the electronic motion that you can look at, and also other types of motion and peculiar particles that we're not going to talk about in this discussion. That statement was based on an experiment following Lamb and Rutherford of that 2s to 2p transition, measuring that frequency and finding that to be 1057 megahertz, 0.13 plus or minus 1.13. Compared to the experiment, that was a theory, compared to the experiment, which had the same error bar, didn't quite agree, but it was also close. And it was clearly a different number from 0. If I was to take the Schrodinger equation for this, I would get a 0, which definitely wasn't right. If I was to take the Dirac equation for this, I get a 0 again. Also definitely not right. If I was to take QED as it stood then, I would get this accuracy, 1, 2, 3, 4, 5 figures of agreement. But if I then look at that Lamb shift and I compare that to the total coulombic energy, the total energy of the system in the atom that you're looking at, which is some 30,000, so 1, 2, 3, 4, 5, 6 and a half decimal places more, then that's actually already, in 1953, quite a lot of decimal places. If I then jump to 1988, then theory has improved by an extra decimal place and a half. And experiment has improved by actually a little bit more. So we now have 10 significant figures of agreement if we take into account the actual fraction of the total coulombic energy that we're actually measuring the accuracy of. I haven't really explained G-2 measurements, except to say that it's basically measuring magnetic moments of an electron. In other words, how an electron responds in a magnetic field. But recent experiments of that, 1987 and 1995 theory, have shown that G factor is 2, almost, but not quite. This guy is basically a constant times alpha over 2 pi, plus higher order terms. And that's been measured to Now I'm obviously deliberately throwing a few numbers at you. But now I'm coming to the statement in the title. In 1997, December Physics Today, in the Munich suburb of Garching, so in Germany, Ted Hench and co-authors and colleagues measured a different transition between a 1s and a 2s state. Now if you remember, S states are the ones where you see the largest amount of QED shifts, because they're the ones that have a probability of having the atom, the electron found near the nucleus, which is where that shift in the potential makes the most difference. And they measured this to that many significant figures. And just in June, I'm glad we had that meeting anyway, otherwise the July lecture would have been a bit different. Would have been that much different. We've now actually, they've improved their technique and they've made a major new development, which is now at 15 significant figures of accuracy. What he says is it's so accurate that simply repeating the measurement a year from now would provide a very precise determination of the constancy of that alpha constant over time. Some people have said it might vary. Dirac said that it might vary with time. If it did vary with time, the best sources of data to tell whether it's varying or not currently would be, or prior to that, would be astrophysical sources. You look at a star, you look at the acceleration of different stars, you're going to see something about that. And there are lots of other applications of that, and the further we understand how that impacts upon the rest of our world, the more interesting and more varied the sorts of conclusions you get. But one aspect of having this enormous experimental precision is that you can develop the theory and you can try and see, can I actually predict that? Can I actually get to that same answer? And so you have a whole series of theoreticians trying to work out those very difficult problems that I was talking about. As a consequence of that, there are a range of very precise measurements for hydrogen, which I just showed you, and also for helium. There's a problem with the precision of the experiment now, because of that exceedingly high accuracy, you start to measure the radius of the nucleus. You start to measure the shape of the nuclear charge distribution. You start to measure the polarizability of the nucleus under an electric field, and you start to be worried about the accuracy of that fine structure constant, separate from the actual measurement itself. That's led to a range of different effects. In many electron systems, you're starting to measure correlation effects, which means how two electrons interact with one another. But if I look at the original equations, we find that those QED effects scale very much proportional to the high powers of the elemental atomic number. And that really is one of the keys as to one of the challenges that is with us today. Because even the lowest order terms, those simplest two diagrams with only one virtual photon, goes the power of Z alpha to the fourth, and there are higher order terms to that. Higher order terms are of order Z alpha to the sixth and Z alpha to the eighth. So in other words, if you have a uranium atom, where Z is like 92, compared to a hydrogen atom, where it's 1, then if you look at a system which has a high elemental number, like uranium, then you're going to be able to devise a much more sensitive test of these bits which are difficult to calculate, and difficult to appreciate, and difficult to be able to measure for a hydrogen atom. If I look at QED in the world today, I can summarize it in a picture a bit like this. By looking at atomic systems and a couple of exotic systems, then I can basically say, here's a very precise experiment, and here's another one on hydrogen, here's another one on helium, here's one on helium where one electron's been removed. Here's a gyromagnetic ratio measurement, and here are one or two-electron systems, but with a high Z or a medium Z system by different people. And you can ask whether they are in agreement with current theory or not. And as you do that, you start, if they're medium to high Z, to be able to be sensitive to those higher order effects, those more complicated diagrams that are extremely difficult for the theoreticians to be able to calculate. Hydrogen actually shows a discrepancy at the moment. But that may be because of something about the nucleus. Helium's in agreement. Other experiments have changed in various ways. The G-2 experiment is in agreement. And some of these medium Z experiments in work at Florida, Oxford, NIST, and Melbourne, and Livermore have interesting questions about them, which may mean that they're good places to look. Another outcome of the June conference that I mentioned just now was that there was an exceedingly interesting discussion, which happens every 15 years, about what the actual value of that constant, that alpha constant is, and what the capital G for gravitation is, and what the value of C for light, so that's actually fixed as a constant. So there was a 2000 readjustment of the fundamental constants of nature, which means that they looked at the whole body of experimental data, and they tried to make a self-consistent set of these constants to try and prove that theory could explain the results. The accuracy of that exercise was improved over the last one by, in general, something like a factor of 10 to 15. But it didn't work. The reason why it didn't work is not clear. We don't know the answer. It may have been due to something wrong about experiments measuring the photon radius. Some problem that we haven't understood yet. It may have been due to something about that renormalization problem, which is at the heart of QED. It may have been due to those higher order expansions, those higher order terms, not actually being mathematically as well behaved as the theoreticians would like. Or there may even be something wrong showing up in the QED formless itself. If you like, they're the main choices. In particular, it showed experimental discrepancies of up to 8 standard deviations, which is actually like a lot. You've got to start to be worrying at that point. If I then go to a bit of philosophy from Penrose again, he notes that he loves QED and he loves general relativity. He believes they're the two best theories ever devised, ever understood, but they're actually incompatible. There was a question a couple of weeks ago about what do you do about that. Well, if you combine quantum mechanics and general relativity, you don't get anything. That was actually something relating to the question. However, if you combine QED and general relativity, there is just a chance you may find an answer in developments of understanding of string theory. I emphasize that has not been concluded. We don't know. If there were such a unified theory in one form or another, then it is possible that some of these discrepancies may be resolved. It's also possible that that would be quite the wrong route to go. And that instead of that, you need to be understanding something else about one of these problems. So if I summarize where a few of those issues are leading us, the last few years have actually started to show such fantastic accuracy, both in experiment and in theoretical prediction, that we can start to find problems. We can start to say, we understand this better than we understand anything else, but we don't quite understand it. So if you're saying, if you've got to believe one thing, it might be QED or general relativity, but maybe not both. But even there, you can actually have a serious debate about whether you ought to believe it or how you ought to be thinking about it, how you ought to be thinking about modifying it or rephrasing it. One of the sections about where to look to try and find something going wrong is crucial. Some people have said, this is a few years ago now, that one of the most precise and sensitive ways to test quantum electrodynamics at high field strength, in other words, where you've got high electric fields, where the system may break down where the influence of those extra photons is much enhanced, is to look for that classical lamp shift, that S orbital energy shift in hydrogen ions where you've only got one single electron. Now I've come to the end of my allotted time pretty much, so I just want to give you a hint at what that might look like. This is what that sort of experiment might look like. Here we have something called an electron beam ion trap. This particular picture is of the one at the National Institute of Standards and Technology. As Graham said, it's changed its name. It used to be the National Bureau of Standards. Now it's National Institute of Standards and Technology. And there they have an EBIT. There's actually only a few of these around the world. The first two were in Lawrence Livermore National Laboratory. That's a military installation. You don't get in there very often. And they tend to basically blow them up every so often as well. That's not quite true. Then the next two were with my old group in Oxford and with my not quite so old group in Washington. What this does is, it has an electron beam traveling up here. Just a simple collimated electron beam. It's focused down to a point around about here. And that electric field attracts positive ions. So if you have, say, some vanadium trickling through here, which you've introduced as an atomic vapor, it'll come in and it'll be attracted to that negative potential. As soon as it hits the negative potential, it'll be ionized. It'll be ionized more and it'll be attracted more strongly. So it'll be bound in a small trap around here. You can actually get bare uranium in one of these. You can produce bare uranium and you can make sure that it's a clean spectrum, that it's one charge state, that it's not contaminated by anything else. Makes it a novel source for this spectroscopy. It helps to avoid those thermal effects that were causing problems in some of the early measurements. And so it allows you to do some nice experiments. Now, if I just show you one picture of this, that's all. This is just one picture. Here you have some of those transitions, in this case with 2 electrons. For vanadium, Z equals 23. So the amplification of those higher order terms is 23 to the power of 4 for the lowest order QED effects, 23 to the power of 6 for the next, and so on. So some of these effects will be able to, some of these measurements, if they're sufficiently precise, will be able to test those difficult terms in the calculation much more precisely. And you end up with a Lambda shift, where you can see this is going to have a Lambda shift and it's got S states everywhere. It's going to have other things in it too, which we're going to talk about. But the sort of accuracy that you get at the moment with that is nothing like that 40 decimal places that I was talking about before. It's about 1 part in 40,000. But that actually lies at the same level as the current uncertainty in theory for these medium to high Z systems. In other words, this is a place where the theory is, if you like, more difficult. Partly because of the need to try to calculate these extra terms and to do it in a self-consistent way. It's therefore sensitive to new types of tests of QED and may actually be the sort of probe to begin to show that something actually is going in a wrong way or having some various difficulties. And it basically leads to a sort of interesting alternate test to try and test QED in a different regime where it may be put in control. This is my last slide, just a summary. It is to say, exciting new developments in theory experiments are happening. QED is a fantastically accurate theory as it stands. There are some problems with it at the moment, which have only really been revealed in the last few years. And in fact, in some cases, in the last couple of months. If we can understand this better by having a very detailed and very precise, interesting type of experiment, we will almost certainly find out a range of new physics, a wealth of new physics, to tell us something about how light interacts with matter, yes, but also to tell us something new about the universe, about the structure of matter, about the electromagnetic force, about quantum mechanics, maybe about relativity as well. And all these different sorts of efforts and investigations tend to be complementary, because until you find where something is wrong, you don't know where to look. Now, having said that, I mean, every decade we have seen QED verified rather than disproven. Every decade we have seen the accuracy increased by a number of significant figures, both on the theory side and on the experimental side. And although there's a significant disagreement at the moment, it may be that if we're trying to work out a comparison between QED and general relativity, or between some kind of grand unified theory or field theory or problem of that nature, we may well be looking, or we may well need to look, in a completely new area yet again. And with that, I'd like to say thank you for your attention.
Thank you very much, Chris. Before I pause questions, take the opportunity of asking one myself. I can give them first, and also give you time to think. But I clearly need a lot of time to think after a lecture like that. It's probably displayed my ignorance of what the whole lecture is really all about. But would you please explain to me how, about 10 slides back, when you gave us the figures for the measurement of the ultraviolet transition between the 1s and 2s states of hydrogen,
Yes.
how do you get the transition between a 1s state and a 2s state, given that S means no angular momentum, and the photon has 1 unit of angular momentum?
It's a very good question. I was trying to avoid complexities of that sort. That S bit is telling you how much angular momentum the state actually has. So both for the initial state and for the final state, the answer is none. But Graham's exactly correct. If you have a photon coming off, you've got an angular momentum of 1. And any way you want to do the arithmetic, 0 plus 1 does not equal 0. That creates two different types of problem and also two different types of solution. One of the ways which has been most widely used is to use two photons, in fact. And those experiments are very interesting and very complex laser optical experiments. So that in fact you have very often a very complex laser, not any kind of a simple laser, not a laser pointer, something which has a whole room full of different laser bits to it, which I didn't think I should put in. But you have photons coming out of that. You also have a mirror on the other end. That mirror means that you've also got photons coming in exactly the reverse direction. If you have an atom just here, in a 1s state, then it is possible, it's not possible to pick up one photon, because then it'll be nowhere. You'll have the wrong frequency to look at the structure, and you won't even get excited in any real sense. But if you have both photons going in those directions, and they hit that, you've got an electric field, of course, and they hit that atom, that electron, at the same time, then you have 1 unit of angular momentum. If I want to deal with this in the simplest fashion, which is not really the right way that I teach a lecture on it, but you could argue that you've got one going that way, one going that way, and they allow you to add 1 and subtract 1. And that allows you to solve the selection rule. That's a little bit of a fudge. But you can ask me a question on that if you like.
Thank you.
Could you give us a simple Feynman diagram for QED interaction and explain in detail how it represents?
Certainly. The simplest one that I showed you was the electron self-energy, which was in a couple of those plots. There you have an electron So this is the electron, traveling, if you like, along in time. Now, the whole concept of there being fluctuations in the vacuum due to this quantum field theory means that you can have a photon being emitted, if you like, by that electron. The mass is a little bit more complicated, and I guess this is not the right place to go into that. You have a photon effectively coming out of that electron, which means that for a certain period of time, that system doesn't have the same average electric field around it than it did before. It has, if you like, an extra unit of energy, or of photon energy, in electromagnetic field, and that's what makes the electron oscillate in position, changes its potential, and causes the shift in energy.
Yes.
Is a wave field three-dimensional?
Yes.
Thank you.
That's the simplest possible answer.
It's not four-dimensional.
Well, if you want to include time and so on,
It doesn't have time.
you don't want to worry about time. Of course, if you want to look at the time evolution of it, then you really have to have time as a variable too.
But you only have time when a wave field collapses, where it becomes discrete.
You can have a stable state which doesn't depend on time. As soon as you have anything involving an interaction or a transition,
And in an application of energy, then you have time.
then you would have a change which involves time, of course.
Right.
Yeah. Yeah. I can also qualify that statement if I really want to by saying that in the Dirac equation, your wave function is a function, let's say, of x, y, and z, and okay, we can argue about what that time is, but this is a complex function. But unlike the Schrödinger equation in quantum mechanics, if you're talking about a wave function in relativistic quantum mechanics in the Dirac theory, then you actually have that as being a sort of a four-component wave function. It's called psi and eta. You never get one without the other. And each of these guys have got, if you like, two parts of them, which tell you about spin. Now, I don't know if that helped.
How much energy is required to collapse the wave function from pre-existing wave field? Is it
Anything you want depending upon the system involved. It can be almost nothing. In fact, there are plenty of systems which collapse spontaneously. They don't actually need any injection of energy.
the energy is pre-existing?
Yes, they're in some kind of excited state, for example.
Right.
Does the low accuracy Electro-Dynamics mean the theory is falling out of favour now?
Not at all. It's almost certainly true, if you define what true is. Obviously I'm being exceedingly critical with QED, right? Quantum chromodynamics is the only real mechanism for explaining a whole wealth of data. Okay? Therefore, just because, and in fact you could argue that about Mendelian genetics and a whole range of the other examples I said, if they are the only sensible interpretation that we have for explaining that part of the data of the world around us, then probably, until we get a better understanding, we should regard it as being true. On the other hand, it may well be that if we increase our accuracy by another 2 orders of magnitude in some of those sorts of experiments, very often the sort of particle experiment that investigates quantum chromodynamics is there a particle here at this energy or not? A yes-no answer. If there is, you better explain it, because it's there. If it's not there, well, you can worry about that. But if it's there at all, then there's something you have to explain. And the best explanation for those exotic particles that you find, and indeed things like quark constituency of nuclei and nucleons, is certainly best explained by quantum chromodynamics. QED doesn't do any of that. It doesn't talk about the strong nuclear force at all. So it can't explain it. You could argue, therefore, that it's going to be incomplete if you look at it, in the same way that you have this conflict between general relativity and QED.
So, you use the change of a 4D as if it was in, or 14 decimal places as if that was impressive. I
I put it to you that that's much more impressive. But I'd like to point out that maths doesn't equal reality. I can have a maths of a certain thing, and that doesn't mean that it's real at all. It's purely real in mathematical terms, not in physical terms. And I'd finish by saying Einstein, the most honest physicist of all time, and he was truly honest because he was honest with himself, he rejected quantum mechanics.
I think there were three comments there. The first one's easiest to address. If you look at the Newtonian Coulombic law, it has the large macroscopic objects, typically astrophysical objects, being tested to a impressive and amazing precision. And in fact, if I go and qualify what I was saying earlier about superb theories, or in fact what Roger Penrose was saying about superb theories of modern physics, he would have classified Newtonian physics as old physics, and yes, indeed, he would actually class that as superb too. But if I'm talking about modern physics, then of course Newtonian mechanics we know is wrong, and we know it's wrong as soon as you go to small dimensions and other problems. As soon as you get to be able to notice the quantum behavior, the quantum mechanics, the quantum mechanical behavior. And Jeff Loper actually gave a number of discussions about the fact that that transition is not nearly as small as it may be. It actually goes to macroscopic or almost macroscopic quantities. Now, of course, if you have a quantum computer, there's seriously macroscopic quantities or situations. So the point is really a different kind of point, namely that just having decimal places in a stupid experiment doesn't really give you anything. Hopefully, the real test is when you have decimal places in an exceedingly good, exceedingly precise experiment. What the 1/r² law in Newtonian mechanics told you was that space is three-dimensional. Now, if you disagree with that, the Coulomb law will fix you up very quickly. And law for gravitation, Einsteinian classical gravitation, will also fix you up very, very effectively. But if you believe that space is three-dimensional, which is then not a mathematical statement but a physical statement, and we'll ignore the multi-dimensional compaction of the early universe just for now, then experimentally we see that for large macroscopic objects we do have a three-dimensional universe in the current epoch, in the current time frame. Second question. Sorry, I forgot. Sorry.
Sorry, you finished on that.
What was the second one, I think?
I thought you got on long enough.
Somebody else.
Last question, speak to the short, it's time we don't move outside the box.
I sort of had some vague, sort of layman's idea that the very act of making the measurement affects itself.
Absolutely.
Like bounce a light bulb, otherwise it affects a lot of the other bounce. But by otherwise, just the existence of the observer somehow affects it even, sort of strange fashion. Where does that affect? What is it? What's the power of effect?
There are two parts to that. One is that it's true, if you make a measurement of anything, which is the same thing as observing, in other words, you get a measurement out of it in any particular way, then you influence and change the wave function that you had there before. That's if you like, a kind of a fundamental. Now, there's a whole range of philosophical discussions and debate around the interpretation of quantum mechanics. And that is highlighted by the sort of Schrodinger's cat sort of thing. If you don't look, is it okay? And if you look, is it dead? And I certainly don't want to discuss that too much in this lecture today. But the answer is some of that, if you like, can be argued to be speculative. Not speculative in the sense that if you had a mixed wave function, complex wave function, and if you observe that to make a measurement, you always reduce that to an eigenstate, to a particular function. You always change it. That's true. Unless it's a completely stable one at the ground state, for example, then it's hard to say that you've actually observed it. But in terms of more esoteric examples of that, like the Schrodinger cat type of idea, then you have to argue that there you have a conflict between macroscopic behavior of quantum mechanics and microscopic.
Could you keep it till after the please and come down and speak to Chris individually? Time is pressing. Time
actual form, means the formal part of the